So the definition of a definite integral. If f is defined on the closed interval a to b, and the limit as your partition goes down to 0 of the sum from I equals 1 to n of f of c sub I times delta x sub I exists, then f is said to be integrable on the interval a to b, and the limit is denoted by this. Okay, the definite integral from a to b of f of x with respect to x. So this limit changes into the definite integral from a to b. Now a is the lower limit of integration and b is the upper limit of integration. So notice this a to b corresponds with the closed interval that we were using in the previous sum. Now, one big note here, a definite integral is going to actually give you a number, whereas an indefinite integral gave you a family of functions. So you remember it gave you a function, but you always had that plus c. Well, in this case, a definite integral, if we know the limits of integration, we're going to come out with a number. So what we want to be able to do is write our limit now as a definite integral. So this is what we've been spending our time determining the sum of, and now we're going to write it as a definite integral on the interval from -2 to 4. Okay, so what we do is we write our integral symbol. Okay, we put our lower limit of integration on the bottom, and then the upper limit of integration on the top, and that's just your interval from -2 to 4. And what we want to do is change any of these c sub i's into x's. So this basically becomes an x, and this becomes an x. Okay, so we're going to write it there, 2x times x minus 1 squared. And I'm just going to put this in brackets here to show that that's our f of x, our function. Then this delta x sub I right here is going to become dx. Just like that. Okay, so delta x sub I, the width of those rectangles becomes dx. And so this now tells us to find the sum, okay, from I equals 1 to n as the partition goes to nothing of 2x times x minus 1 squared on the interval -2 to 4. So let's use the limit definition now to evaluate our definite integral. So we're going to go backwards here. So here's the definite integral from -2 to 1 of 2x dx. Okay, so here's our function 2x, and we're going here from -2 to 1. And so what we're looking for now is the area between the function and the x-intercept in between -2 and 1. And so again, we're going to think about using our rectangles here. And notice our partitions can be anywhere. So I'm just going to draw a couple of them so we can see what we're doing. And let's go ahead and use the fact that we know that our integral from a to b of f of x dx equals the limit of our general partition going to 0 of the sum from I equals 1 to n of f of c sub I delta x sub I is going to equal the limit as n goes to infinity of the sum from I equals 1 to n of f of c sub I times delta x. Okay, so this is the connection that we just made. So let's go ahead and put that in terms now of this definite integral. And let's go straight into this one because this is the one that we can actually find. Okay, so we're going to go ahead and find the definite integral from -2 to 1 of 2x dx, and jumping straight to our limit here. So the limit as n goes to infinity of the sum from I equals 1 to n of f of c sub I. So 2 times, well, we got to find our c sub I. So let's go ahead and do some of that work over here. And remember, before we do any of that, we need to find delta x sub I. And that's just going to be delta x. And so what we're going to do is take our interval and go 1 minus -2 over n subintervals. So that becomes 3 over n. And if we look at this, we're going to use right endpoints. Okay? So it's always easiest just to use our right endpoints. And so in that case, remember we wanted a plus I delta x. Okay, so a is -2 plus I delta x. So that's going to be 3I over n. Okay, so we're going to substitute that in for our c sub I. So that's -2 plus 3I over n times delta x, which is 3 over n. Okay, so this is how you find your definite integral. We've got to find this limit. So let's go ahead and do that work here. We'll distribute everything. Okay. So the 2 is going to go in. So we have -4 plus 6I over n. And now let's go ahead and distribute the 3 over n here. Okay, now let's go ahead and evaluate this sum. We'll still have our limit. So the -12 over n changes into -12n over n. And then the 18I over n squared is going to be 18 times n squared plus n over 2n squared. And if we were to find this limit here, our n's would cancel, so this would become -12. And here, exponents are the same, so it's 18 over 2, so plus 9. And we get -3. Okay, so the definite integral from -2 to 1 of 2x dx equals -3. Now wait a second. Negative? How can a negative number give us an area? Well, it turns out that this is not an area. Now you'll notice one thing we did differently here is that this function fell below, okay, it fell below our x-axis. And so when we found this, okay, we didn't account for our negative numbers. We're going to learn how to deal with that a little bit later.